students, welcome back to the JEE Last Mile Preparation Series 16. Today we will take up questions 31 and 32. But before I do that, by now you already know that I'm Sujata from CBSE NEET JEE Chemistry.in, and we are bringing you 2 questions every day until April 4th to help students get that extra edge for their JEE Chemistry exam preparation. To keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Let's get started. We continue with inorganic chemistry. The questions are chosen from hydrogen and metallurgy, extraction of metals. All right. Let's first look into question number 31. A 5 cubic centimeter of hydrogen peroxide solution liberates 0.508 grams of iodine from potassium iodide solution in acidic medium. The strength of hydrogen peroxide solution in terms of volume strength at STP. So this is a numerical value type question, right? So here we have hydrogen peroxide solution liberating iodine from potassium iodide solution in acidic medium, right? So this helps us to not only do a question to solve and get the volume strength of hydrogen peroxide, this also will help us to recollect some important chemical properties of hydrogen peroxide. You're aware that hydrogen peroxide can act as both an oxidizing and reducing agent. Here, hydrogen peroxide is converting potassium iodide to iodine. In other words, potassium iodide is oxidized to iodine, right? And hydrogen peroxide gets reduced. So hydrogen peroxide is acting as an oxidizing agent. Hydrogen peroxide is acting as an oxidizing agent here. And this reaction takes place in the presence of an acidic medium. Okay, so instead of trying to memorize the whole equation, which involves a reaction between hydrogen peroxide, potassium iodide, and an acid, an easier way would be to quickly understand how that final reaction can be obtained. Okay, in a very, very simple manner. This is how you can deduce the redox reaction. We know that hydrogen peroxide is getting reduced, right? So in other words, it gets converted to water plus nascent oxygen. Now this nascent oxygen is absorbed or gained by potassium iodide. So here we have potassium iodide in the presence of an acid. It could be hydrochloric acid or sulfuric acid, gains this oxygen. Potassium iodide gets converted to iodine, the other product being the salt, which is potassium sulfate and water. So we have to write 2Ki. Now let's add up these two equations, these two half equations. This is the reduction half equation, and the second one is where oxygen is gained is the oxidation half equation, right? So we can easily cancel both the oxygens. So what is the final equation? H2O2 plus 2Ki plus H2SO4 will give you 2H2O plus iodine plus potassium sulfate. So instead of trying to recollect or memorize this equation, this would be easier to arrive at the redox equation, the required redox equation. Now let's focus on hydrogen peroxide and iodine. Now what is the mole ratio? 1 mole of hydrogen peroxide produces 1 mole of iodine. Now in the question, iodine is expressed in terms of mass. Okay, so let's convert these moles to masses. So what is the molar mass of hydrogen peroxide? 1 mole implies 34 grams of hydrogen peroxide, and 1 mole of iodine corresponds to 127 into 2, which is 254 grams of iodine. So what does this tell us? 34 grams of iodine, hydrogen peroxide produces 254 grams of iodine. We know the mass of iodine produced, so we can find out the mass of hydrogen peroxide. which produces 0.508 grams of iodine. So that would be 34 into 0.508 divided by 254. We can simplify this. If we ignore 0 and 8, 34 into zero point 0.5 would be 17. 17 by 254 would be approximately 0.068 grams. So we got the mass of hydrogen peroxide which produces 0.508 grams of iodine. Okay, let's go to another page. So we got the mass of hydrogen peroxide. Now let's write down the equation corresponding to the decomposition of hydrogen peroxide. Because when hydrogen peroxide decomposes, we get oxygen gas. Okay. Now, why are we interested in oxygen gas here? Now, let's quickly recollect what is the volume strength. How do we understand the volume strength of hydrogen peroxide? Now, the concentration or the strength of hydrogen peroxide solution can be determined either by weight percent or by volume strength. So let's focus on the volume strength. According to volume strength, the volume of oxygen, the volume of oxygen gas produced at STP, okay, by 1 cubic centimeter of hydrogen peroxide solution. For example, if the concentration of hydrogen peroxide is 20 volume hydrogen peroxide, what do we mean by this? We mean that it implies that 1 centimeter cubed of hydrogen peroxide solution will produce 20 milliliters or 20 cubic centimeter of oxygen gas at STP. That is the understanding. Okay. So we've been provided with the volume of hydrogen peroxide solution. Okay. And from that, so let's understand the question again. We've been provided with the volume of hydrogen peroxide solution. We found out the mass corresponding to 5 cubic centimeter of hydrogen peroxide solution, which is 0.068 grams. Because it is this 5 cubic centimeter of hydrogen peroxide solution which is liberating this mass of iodine. So we found the corresponding mass of hydrogen peroxide which is 0.068 grams. Okay, so let's see how we can proceed. Now let's write down the equation corresponding to the decomposition of hydrogen peroxide. 2H2O2 gives you 2H2O plus O2 gas. Let's focus on hydrogen peroxide and oxygen. Okay? 2 moles of hydrogen peroxide gas produces 1 mole of oxygen gas. We want the data, the quantity with respect to oxygen, we want in terms of volume at STP. And we have already found out the mass of hydrogen peroxide. Okay, so we will use mass here and we will use the volume here. Now, what is the volume occupied by 1 mole of oxygen gas at STP in terms of milliliters or cubic centimeter would be 22,400 cubic centimeter of oxygen gas at STP is produced by how many moles? 2 moles. What is the mass corresponding to it? 2 into 34, which is 68 grams. Right? Now, we have found out the mass of hydrogen peroxide corresponding to 5 cubic centimeter, which is 0.068 grams. So what is the volume of oxygen gas produced at STP? So let's cross multiply. When we cross multiply, we get volume is equal to 0.068 into 22,400 divided by 68. So this becomes 0.001. So it becomes 22.4 cubic centimeter of oxygen gas. Right? So we get 22.4 cubic centimeter of oxygen gas from 0.068 grams. All right. So that is 0.068 grams. We want the volume of oxygen gas produced from 1 cubic centimeter. So we know that 0.068 grams of hydrogen peroxide corresponds to 5 cubic centimeter solution. So how do we proceed with the calculation? Okay, so now we can say that 5 cubic centimeter of hydrogen peroxide aqueous solution produced 22.4 cubic centimeter of oxygen gas at STP. So, 1 cubic centimeter of hydrogen peroxide aqueous solution produces what volume? So, that is equal to 22.4 divided by 5. So, what is that? 4.48 or approximately 4.5. So, you can say that the volume strength of hydrogen peroxide is 4.48 volume. Just as we say 20 volume hydrogen peroxide, we now call it as a hydrogen peroxide of strength 4.48. Why? Because 1 cubic centimeter of hydrogen peroxide solution produces 4.48 cubic centimeter of oxygen gas at STP. Therefore, the volume strength of hydrogen peroxide is 4.48 volume. Let's go back to the question. So the answer to this question would be 4.48 volume. Okay, so this question also helped you to recollect an important chemical property of hydrogen peroxide and also helped you to understand and again recollect how to arrive at the redox equation instead of memorizing the redox equation. And you also found out how to calculate the concentration of hydrogen peroxide solution in terms of volume strength. All right, now let's move on to the next question. Question number 32, an interesting question again. Now, this is taken from metallurgy. Okay, let's read the question. Extraction of gold is done by the following process. So, two equations are provided to you here. Okay, and you need to identify X and Y. 4 options have been given. So, you have to choose the correct identities of X and Y. So, X would be the first one, this would be X and this would be Y. So you have to identify the correct formulae of X and Y from any of these 4 options. Okay, now just have a look at the 2 equations given here. Okay, now this process is used to extract gold. You know that gold is a native metal, or gold exists in the native state, not in the compound state, because gold is highly unreactive and we call gold as a noble metal. Okay, silver is also a noble metal. So gold and silver are normally prepared by this method, which involves 2 processes. Let's familiarize ourselves with the 2 processes. The first process involves reacting the noble metal, gold or silver, with a solution of cyanide ion. So cyanide ion is a reagent which will react with gold and a complex ion is formed. Now this step is what is referred to as the leaching step or the leaching process, where the cyanide ion is the leaching reagent. Okay, you get a soluble complex. So something happened to our gold. Gold has been converted to another oxidation state. We'll see what that is very soon. Okay, so now gold is in the form of a soluble complex. Now the whatever complex you got here is now made to react with zinc. You know that zinc is a more reactive metal compared to gold or silver, or a more electropositive element. So what does this reaction look like? This is nothing but displacement. So gold is displaced, gold or silver or the noble metal is displaced from the soluble complex by a more reactive or a more electropositive element like zinc. Okay, now these are the 2 steps involved in a process called hydrometallurgy. So hydrometallurgy is the method used to extract gold and silver or other noble metals. So let's understand the reaction better. Okay, so we have to discuss hydrometallurgy. Hydrometallurgy. Step number one is the leaching step. Step number one is leaching process, wherein the gold, here we are focusing on the gold. Gold is made to react with a cyanide ion aqueous solution. So water, a dilute solution, and is made to pass through air, which contains oxygen gas. So gold is in the elemental state, zero oxidation state. Okay. Now here what happens is gold gets converted to Au plus. Au plus. So what has happened to gold? Oxidation has occurred. Gold has undergone oxidation. Now this Au plus will form a complex ion with the ligand here, the cyanide ions. So you get AuCN twice. So let me remove the plus charge there. Okay, you get this complex ion minus 1. So gold is plus 1. This is the two cyanide ions. So minus 2, each has a charge of minus 1. Minus 2 plus 1 is minus 1. So this is the charge on the complex ion, and this is a soluble complex. Okay, soluble complex, all right, and it is referred to as a dicyanoaurate complex. Dicyanoaurate complex. Let me go to a different page. We need more space. So I'm rewriting the first step. Okay. We have to balance the equation. The equation was not balanced. I'll help you to balance it here. Cyanide ion aqueous. Gold is in the solid state. Dilute solution water and oxygen gas. Au gets converted to Au plus, which forms a complex ion. Okay, soluble complex ion. Aqueous means soluble complex ion, referred to as the dicyanoaurate complex. Dicyanoaurate complex. Plus, you get OH minus. To balance this equation, we put 2 here, so it is 4 OH minus. Remember, this is in the ionic state. So if we have potassium cyanide, we will need 8 potassium cyanide, 4 to form potassium hydroxide. So I'm not writing the complete equation here. 4 to form potassium hydroxide and 4 will be here. So this has to be 8. Okay, so 4 will be here because cyanide ion has to be 8, and this will be therefore 4. This is how you balance the first step called the leaching process. Okay, the leaching agent being the potassium cyanide or sodium cyanide aqueous solution or the cyanide ion. Same method is done for silver also. Okay, so this is the identity of X. Now let's write the equation corresponding to step 2. So what is step 2? We've already discussed it. It is a displacement method. So let's see what is happening to the gold ion in the complex. So we start with the complex ion, AuCN twice, minus 1, aqueous. We react it with zinc. Zinc being a more reactive metal, zinc will displace gold. Here gold was in plus 1. You get gold back in the elemental state. So what has happened to gold? Reduction. Gold ion has undergone reduction. Okay. And here you get zinc cyanide ion 4 times, and therefore this is plus 2. Plus 2 minus 4 will be equal to minus 2. Another soluble complex. So we have to balance this equation. 2 here and 2 here. So we call this as tetracyanozincate. Tetracyanozincate 2 ion. Okay, the other one would be dicyanoaurate 1 ion. You have learned how to name the complex ions by IUPAC method. Okay, so this is what happens, and these 2 steps, this is the identity, this is the identity of Y. Okay, this is Y. So these 2 steps together will constitute what is known as the process called hydrometallurgy. Okay, it is a combination of leaching plus displacement. All right. So these are the two steps involved in the extraction of noble metals like gold and silver. So let's go back to the question. So what is the option here? The option A would be the correct answer. All right. So AuCN2, so dicyanoaurate and tetracyanozincate. Okay. If you found today's video useful and helpful, please like the video and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. See you tomorrow.